Okay, let's take a look at how you would do question 3 from the growth problem worksheet. This is the one where you have to use the exponential growth equation, but you have to use it rearranged because it's asking for the number of generations that you're solving, which makes it look like it's a big complicated equation. So again, remember when you're reading through problems, it helps if you pick out the information that you're going to need as you go. So question 3 started saying, we've got a culture of E. coli in the lab. We're going to begin the inoculation with approximately 1,000 cells. So because we're beginning this, we've got 1,000 cells before growth. If you think back to that exponential growth equation, which was little b equals big B, I'll write it out. Remember we had little b equals big B times 2 to the n, where big B was the number of cells before. So big B in this case is going to represent our 1,000 cells. And then we keep growing. It tells us we've got an optimal growth temperature of 37 and a generation time of 20 minutes. So we also had that second formula. Remember, generation time was going to equal the total time of growth divided by the number of generations. So we can kind of make a little note over here so we know that generation time is 20 minutes. Okay. This first part was just to make you guys start thinking of classifications. So we wanted to know, how do you classify? When it asks for that you have, when you have to go back to all those files and trophs and all those words. But we've limited it, so we want to know, how is it classified based on temperature, which should make you think, okay, those were the psychrophiles or mesophiles or thermophiles. So go back to those concepts, look at what the temperature was, and you should have identified that 37 degrees is going to fall in the mesophile group. Okay. What we really want to look at, though, is the math. So let's move on to part B, which is really the math question in this. Okay. First thing it says here is to keep in mind that there's a lag phase of about an hour. And we're going to come back to that later. It's actually not part of the math, but it's to make you start thinking about the phases of growth for bacteria. This is asking us a little bit different question than a lot of them. So this one wants to know, how long would we need to grow a culture? So what we're really asking about is time. If we were going to obtain 1 million cells for the experiment. So remember again, we go back, we scroll up just a touch, where we have 1,000 cells before growth. We now know we want to end up with 1 million cells after growth. And when we looked at our different equations, where little b was the number of cells after, so we know that that's going to be 1 million. And then the problem says, use the equation below to actually solve this problem. And it gives you all the information here about that you don't need lag phase until the end. So let's actually look at that problem. This is the exponential growth equation. So what we have here is, so remember we had little b equals big B times 2 to the n. This equation, rearranged to get n by itself on one side of the equal sign, is the equation that I gave you. So because we've got an exponent, we're going to have to use a lot of logs. I did not expect people to remember how to rearrange an equation to get an exponent on the equal side by itself, which is why I gave you the equation, and I will always give you this one. So if you need to use this equation rearranged, it will be in the problem. Okay. So now we've got n is going to equal, we've got the log of little b minus the log of big B divided by the log of 2. Okay. And we've already been writing numbers down, so we know we've already figured out that the number of cells we want after growth, which was the little b, is 1 million. We're going to subtract that, the log of the cells we started with to start the culture, which was 1,000, and we're going to divide that by log of 2. So I find for students, it's actually a lot easier to do each one of these terms individually and then just do the general arithmetic, as opposed to trying to plug the whole thing into your calculator at once, because it doesn't always do what you think it's going to. And so instead, if you just plugged in log of 1 million, you would get 6. Okay. Minus the log of 1,000 is 3. And the log of 2 is 0.301. So then we just do that math, and you're going to get 9.97, which realistically you could round to 10. Now here's the tricky part, is that a lot of people go, okay, well that was a whole lot of work. I just plugged in a bunch of numbers, I've done all this math, I've got an answer, there we go, I'm done. Except you're not, because what you've just solved for is that n equals 10. And n, remember, is the number of generations. But what the question was actually asking you for, when we come back up, is not the number of generations, but how long you're going to need to grow the cultures. We need a time in here. What we know is that we need 10 generations. To get from 1,000 cells to 1 million cells, the cells are going to have to replicate 10 times. That's what we mean when we say number of generations. How many times have the cells divided? The problem also told you, remember, that the generation time was 20 minutes. And the generation time is how long does it take to make a generation. So if we need 10 generations and it takes 20 minutes to make each one, we're going to multiply those together to say it's going to take us 200 minutes in order to get those 10 generations that we need. Now, I kind of did that in my head because I wanted you guys to recognize the logic of what you're doing. Sometimes it helps a lot to just think about what's happening. And we know that we need 10 generations. The problem told us each generation is 20 minutes. So if we need 10 of them, we're going to multiply those together. What I really just did was use that generation time equals total time over the number of generations to rearrange and solve for the total time. Okay, that would have been multiplying both sides by n, and that's where we got the total time equals generation time times the n, which is exactly what we did to get 200 minutes. Just did it a little bit more in your head so you could conceptually think about what you were doing instead of just memorizing an equation and plugging numbers in. Okay, now again, we're still not quite there. What we just said is it takes 200 minutes to get 10 generations. If we come back up to the problem, we also had this one other piece of information about the lag phase. So if you remember what a bacterial growth curve looks like when we're growing them in standard culture. Okay. Remember, we have lag phase, we have log phase, we have stationary, and we have the death phase. What this question was really saying was if you start a culture with 1,000 cells, how long is it going to be? Whoops, put that comma in the wrong place. Till you get to 1 million cells. Now we want to know what's the time to get from here to here. And we just solved that log phase, because remember, the exponential growth equation can only happen when the cells are growing exponentially. And they only grow exponentially in log phase. So to get from here to here, our 1,000 cells to grow to 1 million, this took 200 minutes. So we just calculated with all of that math and the equations. But the problem tells us this lag phase when they're not growing. So we had 1,000 cells here. Those 1,000 cells are the same cells that are here at the end of lag phase. But this took 1 hour for them to get ready to go, okay, to do all of their gene expression and making all the proteins and to grow in size so they could actually start dividing. And so if it took an hour here and 20 minutes here, our total time would be 260 minutes. Okay, the 60 minutes from the hour and then the 200 minutes that we calculated. And this is how you would use these in real life. So if you knew in the lab that you were starting a culture with about 1,000 cells and you were going to be doing some sort of diagnostic test or an experiment that you needed about 1 million cells for, you would know that if you started that, you could come back about 260 minutes later to get your cells to start your work.